Hello my concrete design friends. In this video we're going to go over a torsion design example using the ACI 318.19 code. This is a class recording, so you may hear a little bit of background noise, but the problems and the steps are all valid. So without further ado, let's get started. So we're looking at this torsion design example. There is one correction to the notes from last time that I need to make. I will get that up on, I will update the sheets on Blackboard, but I'm going to point it out to you in case you have it with you. And it has to do with the equation here in 22.7.7, and that is not in the right spot. Let's get that up there. Oh my gosh, my camera moved on me. There we go. This guy. This equation right here at the bottom of page 2. On the notes, and you'll notice that make sure that the version that you have is updated to look something like this. I have left off a squared on this guy, okay, and then I have left off the square on this one in the original note packet, okay, and it should have been obvious because this is a magnitude calculation. Take the magnitude of the shear stress plus the magnitude of the torsional shear stress and finding the overall magnitude of it. So it's the square of the, the square root of the sum of the squares, if you remember doing that. So make sure this, I will print this, I will get this rescanned and uploaded and corrected up on Blackboard for as soon as we get done with class. The calculations, and I didn't catch it until I was reworking the calculations, and I went, oh shoot. So so as I was updating a practice problem, I was going to kind of work on that. So, all right, here we go. Let me get that out of the way. What page is that? That's that page. Do not need that. Okay, all right. So here's how you put it all together. I've given you a bunch of equations and a bunch of steel details, and I said go. All right. Okay, so the problem that we're going to look at is a kind of a slab type problem. I'm going to pull this out just a little bit, maybe. Okay, all right. Whoops. And of course I hit the camera, and you may get a cat's head to come around the camera here. Get out of the way. You dumb cat's in the office with me today. You off. Okay, sorry about that. Okay, so what we have is, this is kind of a plan view of a concrete framing system. The shaded squares are columns. Okay, and we're not too worried about the dimensions of them in this. Okay, and you'll see that I've got columns all around the perimeter, and then we've conveniently left one off here. So there is no column on this location. Okay, and again, I'll provide all copies of this notes, so don't worry about it. There's a lot of information here, so don't try to jot this down and keep it up. If you want to sketch anything, sketch this guy. Okay, this is, so what's happening is that there are beams that go between the girders, and then this beam ties into this girder, but it does not have a column, so this is going to put a shear load and a torque into this edge beam, and this edge beam is known as a spandrel beam. Right, because it's kind of around the edge of the building and it's spanning between columns. Okay, so you hear that term. We're going to do F prime C of 4,000. We're going to do Fy of 60 KSI on this. Okay, now if I look at a cross section through, at location 1, through that spandrel beam, this is the picture that you get on that. Okay, so what we have is we have a 4.5 inch thick concrete slab that is integral into a beam that is 30 inches tall and 15 inches wide. Okay, and the reinforcing of this is such that the cage, or the area bounded by the stirrup, is 26.5 inches tall. It is 12.5 inches wide. Okay, and the top of this D dimension, if you will, is 27.5 inches up from the bottom. So you've got basically, there's 2.5 inches of cover here. Okay, to get you to the center, not cover, but to the center of the bar on that. Everybody cool with the dimensions that we have? So we've got there's a lot going on here. Now, one thing that we're going to assume in this is, in mechanics, often when you have torsional shapes and then another guy tying into this guy does provide a little bit of restraint and some resistance. We are going to neglect his contribution to the torsional value of the beam. We're going to make the beam do all of the work. And that should kind of make sense. Okay, and I can accomplish that a couple of ways. I could put an expansion joint between the slab and the beam. Okay, or we just, again, this thing's 30 inches tall versus 4.5. This isn't going to provide much. It'd be a few percent, but not a whole lot. All right, so that's our cross section. And we'll come back to using that here in a second. Okay, the next piece that we have is now the loading diagrams. Okay, and so what I've done is I've kind of drawn what's happening on that spandrel beam up in that plan view. Okay, so here's my beam. The girder that's coming across the middle here is putting a vertical shear into the beam, and it's also introducing a moment into it, and it looks something like what you're seeing here. So the vertical shear is 56 kips, that's the end reaction, and it's putting a moment of 121 kip feet into this beam. This is the guy that's causing the torque, in addition to this one. Okay, I did leave off one dimension, so if I do if the dotted line this way is the midspan, the dotted line here is the midspan of the beam, and so there's an eccentricity of that shear force in the amount of 15 inches over 2, which is 7.5 inches. Okay, so you can see that. So this is at the face of the beam that's tying in. So what's happening is a beam is coming in and it's tying in on this edge of the cross section. You guys see that? So it's 15 inches eccentricity from the middle of the beam to the face. So that's the 15. Okay, so 7.5 inches. We'll need that. Okay. So and that reaction is 56 kips. Okay, you've also got the torque that's coming in that from structural analysis you would find that it is 78 kip feet, torque on each end. Okay, if I draw a torque diagram of the whole beam, this is what it looks like. And my cat just jumped in a box. Okay, 78 kip feet. Okay, entertainment, right? Okay, so 78 kip feet here, then it jumps, and then it's 78 kip feet here. So that's the torque diagram from this. Okay, for what's felt in the beam. Okay, and then we've got a crit. This is this is our factored shear here. I left that off. Okay, and the shear reactions would be it's 34 kips of shear at the top, 34 kips at the bottom, and then it comes over and it decreases due to self-weight to 28, and then you get the 56 jump that you're seeing here. So this is the shear diagram that we have happening. Now, again, if you remember from shear, we don't design for the maximum, we design for the shear at a critical location. Okay? And so our critical location are these dotted lines, is located at a distance of D of the beam, which remember that was always D from the face of the support, and then plus H column over 2, because these are all center lines of column dimensions. That's a center line. And then this guy is also, oops, the one that's here is the center line dimension as well. Okay, so if I find the critical value, we're coming in that distance from the center of the column to get to D from the face of the support. So that's 32.4 kips on that. Okay, so those are our diagrams, and we're going to use these values, and I'll show you how to use them here in just a second. Any questions so far? Okay, all right. Okay, so let's go through and we'll kind of talk about, first thing we're going to do is we're going to calculate some section properties. Okay, our goal in this problem is to determine the transverse reinforcement and the additional longitudinal reinforcement required at the critical section at a distance of D from the column face. Okay, that's our critical section. Okay, so we're going to go through, we need to do some section property calculations, and these are all those variables, the alphabet soup that we saw as we were starting to kind of calculate those based on the cross section. So this is now how you calculate those values. So again, remember we're looking at this picture, 15 inches wide, 30 inches tall. So the ACP is basically the gross area of that section. So that's the 15 times 30, it's 450 inches squared. All right. The PCP is the perimeter around the gross area. So it's going to be 30 plus 15 plus another 30 plus another 15. Okay, and so that's our PCP value that we have. So 2 times 15 plus 30, that's 90 inches is our gross perimeter around the cross section. Give me 1 second. I got a dog that's whining. You out. Get out. You in the box. Out. Apologies. Usually she sleeps and the cat jumped in the box and she lost her mind. Okay. All right. Okay. So that's how we get those values. And then ACP squared and PCP over PCP, that's the term that you're going to see repeatedly. So we're going to do that calculation now. That's 450 squared over 90 is 2250 for this. Again, we're just plugging in numbers into equations so that we have them, and we'll make use of these as we move forward. All right. The next ones that we need then are at the ultimate state. Okay, remember ultimate state is when we assume that all of the cover around the stirrups is cracked off and we're only looking at what would be the core that's bounded by the stirrup. So everything outside of that is now spalled away. Okay, and so the area that we're looking at is, we need an A notch or A naught H. Okay, and that's the area that's bounded by what's inside that stirrup. Okay, so that's going to be 12.5 times 26.5. So that's the calculation that we did here. And that value is 331.3 inches squared. So that's the area bound by the stirrup. The perimeter of that stirrup is 2 times 26.5 plus 12.5 or 78. Okay, again, so that's the perimeter around here. Okay, so we got that. And then, of course, I need an A naught H squared over PH. We may need that value, so I'll tally that. And if I do the math, you get 1407 inches cubed on that. Okay, so those are our gross properties for both the uncracked state or the gross section as well as the ultimate, after everything is spalled in our worst possible scenario. We'll need all of those. Okay, so now we can start kind of applying what we've done with the ACI requirements. Okay, and so our ACI requirements on this, it says that you can calculate A naught either by analysis or you can use the shortcut formula. This is in 22.7.6.1.1. We're going to do the shortcut formula. 0.85 times A naught H. So if I plug that in, I get 281.6 inches squared is my A naught value. Okay, everybody cool with that? All right, so now here's where we actually get into design and looking at what is going on with torsion. Okay, the first thing we have to do is we got to figure out, do I even need to consider torsion? Okay, and so we have the code requirement 22.7.1.1 that says that if my applied factored torque is less than my factored threshold torsion, I don't have to worry about it. Okay, so we need to calculate the threshold value. Okay, so this threshold value, T sub TH, is given as lambda times the square root of F prime C times that ratio ACP squared over PCP. So all I've done is I've gone in and I've calculated that value. I got a window in the way. I keep covering half my page. I keep moving it and I don't need to be. Okay, there we go. All right, and so if I do the math on this, you got to watch the units here. Okay, remember F prime C goes in as PSI, and this needs to be in inches cubed, or it will be in inches cubed. So the units that come out of this are 142,302 inch pounds. Okay, because the units that come out of this guy are PSI, and I'm multiplying that by inch cubed. Everybody good with that? Shouldn't be any major surprise. Okay, so that's TTH. I need phi TTH, so I'm going to multiply that value by phi. So 0.75 times 142,302 gets me 106,727 inch pounds. And then I'm going to write this as 106.7 kip inches, just because I'm tired of writing all the numbers. Okay, so far so good? Okay, all right. Now, the next thing that we do then is in order to get my units figured out, remember the torque diagram that was over here was in kip feet. And my design torque is 78 kip feet, so I need to get that into units to be able to compare. So I'm going to take 78 kip feet. I'm going to multiply by 12 inches per foot. That gets me 936. And that units is kip inches. And now I can compare these values. And clearly, looking at these values, TU is greater, much, much, much greater than my threshold value. Okay, so we've got to consider torsion. You knew this was coming, otherwise we wouldn't be doing this problem, right? Okay, but at least we've done the check. Okay, but that's how you do the check with the threshold value. That's the only time you use the threshold value. Okay, is to see if we need to worry about it. Okay, now, one thing that we notice about this beam is we've got to kind of figure out that, if we go back and look at our framing diagram, is this equilibrium torsion or compatibility torsion? The behavior of this guy is affected by the beam, which is affected by the column, which is affected by the beam and the slab and everything else. This is a compatibility torsion case. All right, because all of whatever's happening here, if I allow this to crack and rotate, it will redistribute load over to other parts of the structure. So we're gonna look at basically some criteria in the code that there were two cases. Remember, and depending on whether you were an equilibrium case or compatibility case, you were allowed to design for different values. Okay, so this is a compatibility torsion case. Tells me that we can take advantage of redistribution. Now, we haven't talked about redistribution, and I'll show you what the redistribution numbers look like when we get to the end of the problem, and we won't get there till Monday. Okay, but if we take advantage of redistribution on this, okay, because it's compatibility, I can actually use a reduced torque value. But let's go through the procedure. There are two requirements, and they're located in 22.7.3.1. Okay, the first one says if it's equilibrium torsion, my option when it's compatibility is I can design for the full torque value of 936 and I don't have to worry about redistribution. Okay, again, that's 22.7.3.1. But if I want to take advantage of redistribution, I can actually design for a reduced torque of TU equal to the cracking torque. Okay, well, the question becomes, well, what's the cracking torque? Well, it's 4 times the threshold value. Okay, so I can either design for 936 or I can go calculate the cracking torque value. And that's what we're going to do next, just to kind of show the number that you get. Okay, everybody good so far? Okay, all right. Oops, wrong page. Okay, so here we go. So we're going to compute our cracking torque value. This comes out of 22.7.5.1. It's just the formula. VTCR, again, it's 4 times the threshold value, or you can run the number. So we got 4 times lambda square root F prime C times that ACP squared over PCP ratio. Lambda is the lightweight concrete coefficient, all right? We're going to assume normal weight, so that's a 1.0. If it's lightweight, you'll use the respective lightweight values out of the tables. But again, in this class, we're not going to do much with lightweight. Okay, so I plug the number in, 4 times 1 square root of 4,000 times 2250. I get a number that is 569,210 pound-inches. Okay, and so now we're going to do our factored crack value. So multiply that by 0.75, gets me 426,907 pound-inches. Okay, or 427,000 or 427 kip inches is the factored cracking moment, if you will. And I'm allowed, if I do redistribution, I can design for 427. Okay, that's all this was saying. So I have the choice of designing for 936 or 427. Which one do you think we should design for? Again, it's up to you, but I'm going to choose to go for the lighter one. Okay, we'll have to check the rest of the beam and the redistribution and those effects and see if we have a problem. But let's go with, just for the sake of argument, let's go with this lighter case. Okay, and so that's what we're going to do. So we're going to design for the lower torque. Okay, see what we did? Again, I'm trying to show you all the steps that are in there. Now, what we need to do as we start to find area calculations and do some of our checks, I need to figure out what is my required nominal torque and what is my required nominal shear. Okay, and the way I get that is I take my TU value and I divide by phi. So here's my 427 coming in here, divide by 0.75. The nominal required is 570 kip inches. Okay, the shear, same thing. We take our nominal or our factored shear, VU, which was on that diagram on the front page, at the critical section, divide it by phi. So 32.4 divided by 0.75 is 43.2 kips. That gets me the required nominal strengths that we're needing. Okay, everybody cool with what we did? I'm going kind of fast, but hopefully this all makes sense to you. We're just kind of modifying formulas a little bit, stuff that you've seen before. Okay, all right. Once we have that, now we got to figure out, well, is my cross-section of adequate size? Because remember, there's a check on that to keep us from making the beam too small and then trying to overload it with steel. This is the ductility check. Okay, and so we're going to use this formula, and it's actually 2 parts. This guy has to be less than this guy. Okay, so I'm going to calculate each side on their own. Okay, so this is the applied side. This is the stress that the average stresses that the beam is feeling. This is in 22.7.7. Okay, we have a solid section, so we use the first formula. And this is where I caught the error in my notes before, because I had left off the squared on these when I did it. So this is where the correction came in. All right, so that formula that we corrected now looks like this. Okay, and so we have an average shear stress from the direct shear, and then I have what the shear stress that's coming from the torque coming in here. Okay, and if I plug in all my values, I'm going to take my VU 32.4 divided by BWD. BW is 15, D is 27.5. Again, we showed you those on the front page. And then the TU we said was 427. That's what we chose. Whoops, pull this down a little bit. That's what we chose here, so 427, and then I divide by 1.7. And then I divide by A naught H squared over pH. Now notice this formula is written a little bit different. In the original version of it, pH was in the top, it wasn't in the bottom. But if I refactor it this way, I've now got that quantity calculated from the ultimate section properties when we did it. And we found that number was 1407. That's, if you remember, that was this guy right here. Okay, so we kind of restructured the formula a little bit, but it's the same formula. Okay, and so if I do the math on all this, you'll find out that the total stress from the applied loads is 0.195 KSI. Okay, now we got to figure out, well, what's the total average stress that the section can support? And so that formula was the other side of the equation is phi times VC over BWD plus 8 root F prime C. Okay, now again, you got to kind of watch your units on this. Okay, and so first thing we do is we calculate VC. This is the old 2 root F prime C BWD formula that you remembered from shear. Okay, so that's no problem. If I plug all of that in, the shear concrete capacity is 52.2 kips. Okay, and so I can plug all of that in. Okay, and so we got to kind of watch our units. So the units on this are kips. So I'm going to calculate this formula. So the phi is 0.75. Here's the 52.2 kips. B is 15, or BW is 15. D is 27.5. That's the first term. The second term is 8 times the square root of F prime C. Remember, that gets me a PSI value. I'm now sitting with KSI here, and I have PSI here. I've got to convert this to KSI. So you're going to do 1 divided by 1,000 on this piece, and that value is 0.474 KSI when I do the math. You guys with me? So if we look at it then, we take my 0.195. Is it less than this value? It is, so my dimensions are okay. Okay, if you fail this check, you have to resize B and D and then redo the calculation. Your section just isn't big enough. You'll over-reinforce it, and it won't be a ductile failure. It'll be a brittle compressive failure when things go bad. So you've got to do this check. You're always doing this one. Okay? Any questions on what we did with that? So it's just a straight plug and chug. You can see everything we've done so far has been pretty straightforward. You can build a spreadsheet really easy for all of this, and you have some inclination of what's coming at you on the homework assignment when I give it Monday. That's what you're going to be doing. Okay, is being able to plug this stuff in and kind of quickly run these numbers down. Okay, so that's why I'm writing all of this out in detail. I'm going to have you guys enter this one into the spreadsheet as a test case, and then we're going to generalize it and do some other things with it. Okay, does that make sense? All right, questions, thoughts, comments on that? Nope. All right, so that's where we're at. I know we're going fairly quickly through it, but it's still taking some time. Okay, so now we've got to the point where, okay, we know what our cracking torque is, and so we're going to go through, all we're going to do today is just look at the transverse steel, because there's some things that happen further on down that we got to look at, and then on Monday we'll do the longitudinal requirement. But what we're going to do is we're going to assume a theta of 45 degrees for our truss model, okay, and we know that from our transverse steel equation that the nominal capacity T is equal to 2A naught times the transverse steel area times its yield stress over the spacing multiplied by the cotangent of theta. Okay, and that's the equation in 22.7.6.1. Okay, because remember the way the code is written, it says, well, torsional capacity is the lesser of the transverse equation and the longitudinal equation. We're going to go under the assumption that the Tn is the same for both, and we'll solve for AT over S and AL over S on that. Okay, but I'll show you that again. I'll show you that piece on Monday. So all I'm going to do is I'm going to take this equation and I'm going to rearrange it, and I'm going to solve for AT over S. Okay, so AT over S is going to be Tn over 2A naught Fyt times 1 over the cotangent of theta. And you have all of these values. We've tallied everything that you need, so it's now just plug and chug. We found Tn as 570 kip inches. A naught, we computed that with the 0.85 shortcut formula as 281.6. So 2 times A naught times Fy of 60 KSI times 1 over the cotangent of 45 degrees. All right, and so this AT over S ratio is 0.017 inches squared per inch. Okay, so if we go in, we can kind of start to, in fact, I'll write this down on another page, that if we have a number 3 as my AT bar on this, okay, that would be 0.11 inches squared, okay, and if AT over S is equal to 0.017 inches squared per inch, then my S spacing that's required for a number 3, let's turn that a little bit so it's not quite looking sideways on you. See Elijah tilting his head up there. Okay. So I can now say that my AT value is going to be 0.11 inches squared all over 0.017 inches squared per inch. The spacing required on that, if I do this number, 0.11 and 0.017 divide, this would be 6.47 inches, okay, is the required spacing on this. So that would be a maximum value for strength. So you have to provide something less. So I'd probably go in and call this as 6 inches. So my number 3 torsional stirrups would be spaced at 6 inches on center or something less than 6 inches. Now again, we're going to play some games with the shear and kind of combine these two, but that's how you're using this AT over S calculation. Okay? See if you guys can do the number 4 calculation. See if you can write me the formula, and then we'll do the math together. Oh, I just wrote the same number down. What's the AT for a number 4? Do you remember? Should be 0.2 inches squared, right? All right, so again, AT over S is still constant. That's 0.017 inches squared per inch. So the spacing required for a number 4 for the torsional steel would be 0.20 inches squared all over 0.017 inches squared per inch. And that number is 0.2.017 divide. Should be 11.76 inches. All right, so, you know, probably an 11-inch spacing. That's kind of an ugly number, really. It's like so close to 12, but not. So drop it to 10, drop it to 9. It's kind of a weird spacing, but that's kind of where we're looking, how I would start to choose those. So you can see a big difference in the size of the bars, what they do on the spacings, right? Okay, basically you cut the number of bars you need in half by going to a number 4. Okay, and that's a pretty standard stirrup size for a lot of beams as a number 4. Okay, it's kind of optimal. Okay, all right. Okay, so what do we do with this value now that we've got it? Okay, and that's where we got to kind of look at. We are still bound, so we know what we need for strength. But if you remember, back in when we were doing shear, we were also bound. We went in and we found what's the situation for the transverse steel for shear. Okay, well, we checked for strength. So my VN required is 43.2. Okay, my VC we said was 52.2 kips. So if you remember, what this is telling me is that VS is equal to 0 on this. Okay, but I do need a minimum amount of steel. Because remember, if I go less than VC over 2, I don't need any stirrups. But if I'm and if you remember, that kind of comes back for the diagram that we drew. It looks something kind of like this, that we had a series of lines, if you remember. And this was my cross section. And again, this isn't exactly what my shear diagram looks like, but it's close. Here is my critical section, D. Okay, so that's my VU at D. So this area would require stirrups, and then from here to here, this is a minimum stirrups. This is none. Okay, and this is where I need VS, extra steel provided to get the capacity. Remember that diagram that we drew? I hope. Okay, do you remember what these two lines were? That one's VVC, and the one below it is VVC over 2. Okay, so that's the picture. And again, I'll provide you a copy of this. You have this in the packets from the last class anyway. But all right, so that's what we have. So if we look at what we have on our picture, my VN required is 43.2. My VC is 52.2. Well, VC over 2 on this would be 26.1 kips. So we're in between those two. So we're living in this range here. We're down in here. Okay, and that's how I knew that I needed a minimum amount of stirrup steel on that. Okay? Okay, so because I need that minimum in there, we've got to go in and figure out, well, I don't need any technically for strength because our VS is going to be 0. Okay? But I do need a minimum amount. So this is where we come in and we look at our minimums. And if you'll remember, you'll recognize these two formulas when we did AV over S. Minimum was this. Well, now when I throw torsion into it, I can count the torsional steel as part of the minimum for the shear. Because I don't need it for strength, but I need a minimum amount. So instead of doing AV over S is equal to this, or AV over S minimum is equal to this, I'm going to add in the torsional piece to it. So it's 2AT over S plus AV over S, and the minimum value when I run this number out, 0.75 square root f prime c bw over fy, I plug in all my values. Again, bw is 15. Okay, I get a number of 0.0119 inches squared per inch. Okay, is the minimum that is needed for the first case, and then I check the second case, which the difference is the formula is now 50 bw over fy. And if I do that, that minimum is 0.0125. Okay, and if I do that, the largest controls. All right. So my minimum amount of steel is 0.0125 inches squared, per inch is the minimum that I have to have in the section. Okay, so now we're going to go in and figure out, well, how much did we give it? Okay, so this is the minimum check for the steel requirements. Okay, so if we look at the total transverse reinforcement needed, okay, well, let's go look at what strength told me. AV over S plus 2AT over S would be equal to 0 for the direct shear. So the first term is the direct shear, the second term is the torsional value. Okay, and because we have double, it's a closed stirrup, we only count on 2 of the legs of the torsion. So we said that an ATS value that we needed in my original calculation was up here at 0.017, right? When we did the calculation for the strength. That's coming out of this TN formula. Okay, so that's what I needed for torsion as AT over S. The total that I gave it is 2 times that value. So 2 times 0.0168, this is the number I rounded it to 0.17. Okay, it's the same value. And if I do that, this is 0.0337 inches squared per inch is what I've given it. You guys see what I did? The hardest part to wrap your head around in this whole process is that 2 that hangs out here and the difference between an AV and an AT. Okay, but you still got to do the minimum check. Any questions on that? All right, so 0.0337 inches squared per inch, so we've got that. And then, so if I do the math on, so my minimum is 0.0125, I gave it 0.0337. So clearly, what I gave it is more than the minimum. We're okay for the steel that we've designed for. You're kind of seeing it? And so that's where we could go then and start playing with, oops, maybe I lost the page. Is it on the bottom? There it is. Now is where you would go in and you would start playing this game. Choosing your sizes, choosing your spacings, and figuring it out from there. Okay? Any questions on that? Okay. All right. So I'm going to pause there. The next thing that we've got to check, we've got 2 other steps that we've got to do, and I'm going to do both of these in our next meeting, on the next video on this, is we've still got to come in. We've done the transverse reinforcement. Now we've got to go in and do the longitudinal requirement. Okay, but because we're going to choose an AT over S and set that value, and then I'm going to set that value into the longitudinal area requirement to get the calculation. Remember how we manipulated that formula and set the 2 TNs together? And then I could write one in terms of the other. And so that's what I'm going to do. And then with that, we'll be able to get our longitudinal requirement. And then the finale of the problem is we'll go through and we'll do the detailing, okay, and figure out, well, how are we going to spread this out around the section? Do we meet all the spacing requirements and the distribution requirements and so forth and so on? And we'll go through all of that on our next class period. All right. So anyway, if you got any questions, give me a holler, leave a message down in the comments below, subscribe to the video, all of our usual, and we will see you guys next time.